Today we're going to show you how we compared 5 friction factor estimation theories for laminar and turbulent flow in pipes. This involved using a hydraulic bench to measure the flow rates, velocities, and head losses. For this experiment, our purpose was to determine the best approximation method that can be applied when estimating the friction factor in pipes. This can be applied in the design for smooth pipes or more accurate use in the greater academia. Results from this experiment will aid in the future use of theories in academics as well as applications for this type of apparatus. To be able to perform this kind of experiment, we used the TecQuipment friction loss in a pipe apparatus attached to a hydraulic bench. To determine the best approximation method that can be applied to estimating the friction factor, we found the closest fitting relationship to the experimental values. The method includes theoretically calculating the Reynolds number and applying it to the research approximation theories, then determining the closest fitting relationship to the experimental values, one of which we applied for laminar flow and the other flow we applied to using the friction factor determination for turbulent flow. Other than the TecQuipment friction loss in a pipe apparatus attached to a hydraulic bench, we used 1 liter graduated cylinder, 2 stopwatches, a thermometer, and a water collection vessel. The 4 variables that we collected when experimenting and collecting data were the temperature, time, volume, and the head loss. As pictured, the H7 apparatus was set up connecting the header tank to the system along with both the inlet and the outlet. Before running tests and collecting data, we made sure to bleed the system to remove all air bubbles from the system, especially in the manometer. Once water moves vertically up the apparatus into the header tank from the inlet pipe, the header tank fills with water, goes down the outlet pipe, and then into the manometer to measure the head loss. After that, the water makes its way to the flexible outlet pipe, which it is then collected by a vessel and dumped into the measure vessel to record the volume. The time was also recorded to calculate the velocity in the system. As you can see here, my finger is following the pipe to show you the flow of water and where it goes throughout the system. For the turbulent flow experiment, we made adjustments to the H7 apparatus by removing the header tank along with its inlet and outlet pipes. For this setup, water immediately runs from the H7 apparatus into the bleed pipes to the manometer, and then from the manometer it leaves through the flexible outlet pipe when it is then collected by a vessel into a measuring vessel to record the volume, and the time is also recorded to calculate the velocity in the system. As you can see here, my finger follows where the water flows within the system. In each of the listed equations, L is the length of the pipe, H is the head loss, V is the velocity of the fluid, D is the diameter of the pipe, and G is the value of gravity. The theoretical Darcy friction factor for laminar flow is given by Powelly's law. These values are produced with the Hagan-Powelly equation. The friction factor is calculated using the Reynolds number. There are several accepted theoretical equations used to calculate the friction factor, including the Colebrook equation and the Blasius equation. For laminar flow, the experimental friction factor is determined using the Weisbach's equation, derived from the correlation between head loss and pipe dimensions. The von Karman equation assumes that the pipe is absolutely smooth. The Kuh equation is proposed from his experimental data of turbulent flow in a smooth pipe, largely derived from the Blasius equation. To determine the experimental value of the friction factor, Weisbach's equation will be utilized. The experimental results compared very well to a few of the turbulent flow expected values with the exception of the von Karman equation. And the results for the 4 approximation methods showed low % error, proving that they are good approximations for a friction factor with turbulent flow. The friction factor for laminar flow using the Hagan-Powelly equation yielded much higher error than expected. With this being well accepted equation, the error comes from the experimental friction factor rather than the approximation. The slight downward trend in error suggests that the trials with the lowest flows are most reliable, with the smaller error correlated with the higher Reynolds number. Our graph shows the friction factor versus the Reynolds number for each trial. The graph allows us to analyze the trend line between the laminar and turbulent flow rates. For laminar flow, the result should fit a linear relationship since the Hagan-Powelly equation has a consistent number divided by the Reynolds number. The graph also shows how in turbulent flow rates, the trend line decreases, which means the Reynolds number increases. The friction factor will eventually become constant and independent of the Reynolds number. These findings underscore the importance of carefully selecting the appropriate equations and models when dealing with fluid dynamics and engineering systems.